In the middle of Shenzhen, robotic arms now froth milk and serve coffee to crowds of daily commuters. These retail displays are the first phase of a national strategy to integrate humanoid machines into the consumer market. The government has enacted a national mandate to build a world-class, mass-market humanoid robotics industry by 2027. Historically, robotics development faced a significant bottleneck. For decades, machines were built for narrow, specific tasks, which prevented them from reaching the economies of scale required for mass adoption. The human body provides the solution to this scaling problem. Because our physical world, the stairs, tools, and doorways, is built specifically for us, the human shape functions as the most versatile form factor for a general-purpose machine. This chart illustrates the economic logic behind that form factor. It compares the high cost of producing 10 specialized machines against the efficiency of a single humanoid design. By perfecting one generic shape, manufacturers produce millions of identical units, causing the cost to plummet. Reaching this level of mass production requires solving three specific engineering challenges: mobility, intelligence, and dexterity. The first pillar is mobility. Bipedal walking is difficult to replicate because it requires a machine to maintain a continuous state of controlled falling. To ensure these machines operate in the real world, researchers kick and punch the robots to force them off balance and test their recovery speed. The machine does not rely on a pre-programmed recovery animation when it is hit. Instead, the robot uses an internal algorithm to calculate its center of gravity and teach itself how to adjust its weight in real time. Mastering this autonomous balance is a strict requirement. Without it, a 50-kilogram machine cannot safely move through a factory or a home. The second pillar is embodied intelligence. This is the process of giving an artificial intelligence a physical body and forcing it to learn through trial, error, and direct experience in the physical world. While AI has mastered the digital realm, it lacks the perception and motion control data required to interact with solid objects. To gather this data, developers use human teleoperators. These workers wear VR headsets and use joysticks to remotely control robots as they perform basic chores like folding clothes or sorting items. During these sessions, the system records thousands of hours of camera footage, force sensor feedback from the hands, and motor control signals. This massive dataset enables few-shot capability in the underlying foundation models. Few-shot capability is a feature that allows an AI to adapt to entirely new tasks using only a small amount of new input data. Forcing AI to learn through a physical body is currently the only way to train machines to handle the unpredictable nature of our environment. The final biological pillar, replicating the human hand, presents a significant engineering challenge. Our hands possess over 20 degrees of freedom, a term referring to the number of independent ways a joint can move. This schematic shows the hardware to mimic human touch, identifying precise locations of tactile fingertip sensors and knuckle force sensors. They facilitate a closed-loop control system, constantly feeding pressure data to the processor, allowing the hand to adjust its grip and safely handle fragile objects. Traditionally, packing this many specialized motors and sensors into a small mechanical hand was too expensive for mass production. The industrial landscape of Shenzhen provides a solution. The city combines rapid software prototyping with dense manufacturing infrastructure to lower development costs. China is also recycling components from its electric vehicle boom. Batteries, sensors, and assembly line hardware developed for cars are now being repurposed to build cheap robot parts at scale. By utilizing this existing supply chain, manufacturers can assemble highly capable humanoids at a fraction of their historical cost. These machines will first be integrated into controlled environments, like factory floors, where tasks are repetitive and predictable. The second phase involves semi-controlled public spaces. In grocery stores, humanoids will handle logistics and restocking shelves alongside human customers. Developers expect these machines to enter the human home within 3 to 5 years to perform daily domestic chores. As the hardware, wiring, and AI foundation models converge, the adoption rate is expected to rise rapidly. These machines provide consistent labor without the fluctuations in quality that affect human manufacturing. Their integration will shift the baseline of global societal productivity. As autonomous humanoids become as common as smartphones, we face a new societal question. We are moving toward a reality where children may spend more time interacting with machines than with people.